Welcome to Weller Physics, where weird is the rule, not the exception. In this video, we'll explore quantum mechanics from wave-particle duality to the rules that govern electrons and atoms. Get ready to explore the bizarre, beautiful logic that powers the universe at its smallest scale. Let's get weird, y'all. The photoelectric effect will be our first foray into quantum mechanical phenomena. The photoelectric effect describes how electrons are emitted from a metal when we shine a laser light on that metal. Essentially, when we send different colors of laser light, eventually, if we get to a high enough energy laser that is incident upon the metal, electrons will be ejected from that metal. These electrons have a maximum kinetic energy that we can calculate as being the difference between the energy of the incoming light minus the work function of the material. The work function describes the minimum energy needed to eject an electron from a metal, and we can calculate this as Planck's constant times a frequency. And so different metals have different work functions because it's easier or more difficult to remove an electron from certain metals. So when we set up a circuit to measure these electrons and what energy they have, we can set up a system like you see above here, where we have an ammeter used to measure the current from these electrons that are emitted, and we have a voltmeter to measure the ultimate potential difference that we can establish based on the energy of the electrons. The stopping potential, V0, is the amount of potential or voltage needed to slow down these ejected electrons and cause them to completely stop. In other words, we would need to establish a potential difference that would cause for the energy of the electrons to exactly match the kinetic energy that they were ejected with. And we noted that specific energies are required to actually emit an electron from a metal surface. This means that there is a threshold frequency or a cutoff frequency, F0, which is essentially the frequency of light that is required in order to eject an electron. In this example, you'll see that red light does not cause for an electron to be ejected, and then for this material that has a work function of about 2 electron volts, the green light does emit some electrons with a small amount of energy, and as we increase the energy of the incident light from there to blue light, we'll see that the electrons are ejected with a greater kinetic energy. In this way, we could measure the energy of electrons emitted based on the frequency of incident light that we expose the metal to. And we notice that no electrons are emitted. There's no kinetic energy possible to impart on the electrons until we cross over some threshold frequency. And this will be different for different materials because they have different work functions. And we also find that regardless of the intensity of light, whether I'm shining bright light or dim light toward this metal surface, the ultimate stopping potential ends up reaching the same point, regardless of the intensity of the light. What this means is that if we increase the frequency or wavelength of the incident light, then we can impart more energy onto electrons that are emitted, but there will be no change in the current that's observed. As we shine a different frequency, we're assuming the intensity of the light stays the same, and so we get a higher stopping potential, but we observe no change in the photocurrent that we measure. On the other hand, we could imagine shining the same frequency or wavelength of light at a higher intensity, a brighter intensity, and what that would do would lead to no change in the kinetic energy of the electrons emitted. An increased photocurrent would be measured here. So an increase in intensity leads to an increase in current measured, more electrons, but it ultimately doesn't change the energy of those electrons. We now witness our first point in quantum mechanics where something is starting to behave a little bit weird. I thought light was a wave. I thought waves could go through things. They can transmit through a boundary and be reflected off of that boundary, and they continuously disperse their energy into a medium as they propagate through that medium. But that's not what we're seeing here. What we're seeing here is it's like a packet of light is hitting an electron in a material and ejecting that electron. This is different than how waves behave. Waves do not run into something and then impart all of their energy onto it such that it is ejected with that energy. Instead, waves impart some energy toward an object as they pass through it, but they don't actually fully impart their energy as they would as if they were experiencing a collision like a billiard ball would. In other words, the photoelectric effect indicates that light is not actually a wave. It's behaving more like a particle, actually. And we would say that light has a particle-like nature. It can experience collisions. There's a conservation of energy between the two objects that collide. And we only see this particle-like nature under certain conditions. In this way, we could say that the energy of light is concentrated into small, discrete packets of light. And we call this a quantum of light. Essentially, it's the smallest amount of light energy that I could possibly get. There's no way I could divide light into a smaller amount than a single photon, which is the quantum of light. It's the smallest possible discrete unit that we can have for light. And so now our understanding of intensity is starting to make a little bit more sense. The light intensity in a light signal is proportional to the number of photons in that light source. And that's why when we shine a higher intensity onto a metal, that there are more collisions and more electrons end up being emitted. But those electrons are emitted at the same energy based on the incident light frequency. And so the energy of a single photon can be said to be equal to Planck's constant times the frequency of that photon, and we could rework to be in terms of wavelength as well if we wanted. All right, so let's try an example with the photoelectric effect to figure out how some of these equations work. Light is incident on a metal surface with a work function of 2 eV. What is the threshold frequency for this material? And what is the maximum kinetic energy imparted on photoelectrons when the frequency of incident light is 6 times 10 to the 14 hertz? And also, what is the stopping potential for these electrons? So let's go from the top. To calculate the threshold frequency, we're going to need F0 equals question mark. To calculate the maximum kinetic energy, K max, that would be like calculating the left side of the photoelectric effect equation. So that'll involve basically calculating 1/2 mv squared. That would be the difference between the incident light frequency energy and the work function. And then lastly, we're asked to calculate the stopping potential. And so let's go ahead and try solving for some of those. Okay, so there's our calculations for this problem. Most of the calculations are actually rather straightforward, but it does take a sec to get used to the units. Notice in this problem that I stuck with using electron volts as my unit for energy everywhere. The electron volt is a very small amount of energy. The energy somewhere on the scale of like what electrons feel. It's like 10 to the minus 19 joules. Joules are a macroscopic unit of energy, and electron volts are a much smaller quantum mechanical unit of energy. So often you'll want to leave your units of energy in electron volts. And some reasons why this is more convenient is because often the numbers are on a scale that's much more reasonable. Here our frequency is times 10 to the 14 hertz, no way around that one. But you'll notice when we calculate our kinetic energy, if we just leave it in units of EV, electron volts, we get a number of like 0.481 EV rather than something times 10 to the negative 18 or 19 or 20 joules. And then furthermore, one other thing that's convenient about using the electron volt is when you calculate your energy in electron volts, calculating the stopping potential at the bottom is just as easy as dividing an electron volt by the charge of an electron. And that will naturally remove that electron and just cause for the electron volt number in energy to be read as a voltage. To understand anything more about quantum mechanics, we will need to begin to develop a picture of what we think the atom actually looks like. How do the electrons orbit around the nucleus of the atom, and how are the protons and neutrons sitting in the nucleus to lead to that orbiting? The Bohr model of an atom describes the quantized energy levels that electrons sit at. Essentially, Bohr postulated 2 points. He said that orbital angular momentum of electrons is quantized. Now, what that means is that electrons can only orbit around the atom at specific orbital levels. Maybe this would be like level 1, and then there's no in between 1 and 2. The next orbit would always be a certain size at a certain energy. That's essentially what this statement is saying. And so, Bohr's second postulate was that when electrons jump between these different energy levels, they release or absorb an amount of energy that is equivalent to the difference in those energy levels. Essentially, the lowest energy that an electron could possibly occupy in an atom is called the ground state. That's the lowest energy, E1 or E0. And every time an electron jumps from one orbit to another, one orbital level to another, it will either absorb or emit a photon with the same amount of energy as the difference between those energy levels. And we can calculate the difference between those energy levels and set it equal to the energy of a photon that is absorbed or emitted. To track the different orbital levels of electrons in an atom, we're going to begin to understand our idea about quantum numbers, starting with the principal quantum number n, which essentially designates the energy level of an electron at a specific quantum state. Essentially, the hydrogen atom will be our easiest atom that we could possibly study. That's just got one proton in its nucleus and one electron orbiting around it. So it's relatively easy to calculate the electrostatic attraction between the negatively charged electron and the positively charged nucleus with the proton in it. And therefore, we can calculate the radius of that atom when our electron is at the ground state, E0. The Bohr radius is a number that defines the radius of a hydrogen atom with one electron resting at the ground state level. Half an angstrom would be the size of the Bohr radius. And then as our electron in the hydrogen atom jumps to higher energy levels, it would also be expected to have a larger orbital radius. And we can say something about the atomic size of a hydrogen atom based on the energy that the electron is at. And the radius of a hydrogen atom for an electron at a given energy level n can be solved for by being n squared times the Bohr radius, where n is a principal quantum number that can adopt any integer value greater than 0. So we could have our electron at the n equals 1 energy level, and we would have the Bohr radius for our atomic size. But if our electron is at a higher energy level, that makes our atom larger with a larger atomic radius, and we could calculate the atomic radius with this equation. And we can calculate the energy for an electron at a specific quantum level n by relating it to the ground state energy. The magnitude of the energy of an electron at its ground state is 13.6 eV, and at the n equals 1 quantum state, that number would be negative 13.6 eV because there is an electrostatic attraction between the negatively charged electron and the positively charged proton in the nucleus. And we can use this formula to calculate the energy of an electron at any quantum level n by relating it to that ground state energy. Essentially, the energy of an electron will always be negative because it's attracted to the nucleus, but the energy gets closer to a value of 0 as we step up to a higher quantum level n, and that essentially means that it's easier to remove an electron that's at a higher quantum level because it has less energy binding it to the nucleus. The ionization energy is the amount of energy required to remove the outermost electron in an atom. And so that means that we're essentially going to take our electron and bring it to a quantum level infinity so that we can essentially remove all of the energy from that electron and pluck it off of the atom itself. And so the difference in energy for this transition would be about the same as the energy of the electron. We would just need to input a positive energy to match the energy of the electron at some quantum level, and that would cause for that electron to be ejected and the atom to be ionized. We notice that the energy levels in our hydrogen atom are not evenly spaced. Down here at n equals 1, we have negative 13.6 eV being our binding energy, and so we would need to supply that much energy to ionize an electron from the ground state of hydrogen. But if the electron is at a higher energy level, then the energy difference required to remove an electron ends up becoming lesser and lesser as we go to higher quantum levels n. So far we've only spoken about hydrogen and how we can use quantum mechanics to map out the different energy levels of electrons in hydrogen, but we can also think about hydrogen-like ions. These are the simplest type of atoms that still just have one electron being attracted to a central nucleus with a positive charge. So this is a basic electrostatic attraction problem. So an ion like lithium 2+ would still only have one electron, but instead it would have 3 protons ultimately in its nucleus that was dictating the electrostatic attraction, keeping that electron orbiting around the atom. And Bohr's model of the hydrogen atom still works pretty well for these atoms. We can use the formula for the electron at some quantum level n for a hydrogen-like atom, where Z is the atomic number with the number of protons in the nucleus being Z for this equation. And so as we step up to along the periodic table to larger atoms, if we ionize them such that they only have one electron, then we can still use Bohr's model to accurately depict the energy levels of an electron at different quantum levels n. One way that we can measure and notice these different energy levels of electrons within atoms is by measuring absorption and emission spectra. These are basically ways that we can shine light at a specific material, and whatever light makes it through, we know is not absorbed by that material. Or if we excite some type of material, we know that the photons that are emitted, the energies of light that are emitted, would also be correlated to the different energy levels within that atom. So absorption spectra show dark lines on a projection screen. When we send light through some type of gaseous material, the light at certain wavelengths will be absorbed, not making it through that material. And everywhere where we see a dark spot would indicate some energy level that was exactly correlated to the energy differences within the atomic structure of that material. That's an absorption spectrum. But an emission spectrum would be if we had a material in some type of tube that we excite, maybe we send a spark through it or something like that to excite the electrons to a higher energy level, and then those electrons will relax down to a lower energy level and emit a photon at a specific wavelength, and only specific wavelengths of light would show up on a projection screen. And these specific wavelengths of light would also be correlated to energy differences within the material. So we'll see for hydrogen gas here, H2, that it has a relatively simple absorption and emission spectrum that match each other. Essentially, the absorption is the inverse of the emission spectrum for hydrogen gas here. And so we can match up each of these lines in the spectra with a specific energy transition between different quantum levels for electrons jumping from one quantum number to another. We contrast these spectra with continuous spectra, which is what you see when you look at a light bulb. Essentially, as we heat up the filament in a light bulb, we allow for many different energy states to be present for electrons in that material, and that means that the electrons can be excited and relaxed down across many different wavelengths and many different energy transitions. And ultimately, we would see a continuous spectrum for objects that were experiencing black body radiation. Essentially, as we heat up an object, it will display a continuous spectrum rather than a specific characteristic absorption and emission spectrum. Since the energy levels within an atom are fixed and electrons can only jump between specific energy levels, they cannot have energy anywhere between those levels. That means the difference in energy for an electronic transition can be calculated just based on the difference in the final and initial energy states. We had an equation that was used to calculate the energy of an electron at a specific quantum level n, and so if it jumps between levels, we can calculate the difference in energy, and we can match that energy to a characteristic photon that was either absorbed if the electron jumped to a higher quantum level, or a photon that's emitted if the electron jumped down to a lower quantum level. The frequency of light emitted can be calculated using the Rydberg equation, where we have RH as the Rydberg constant. Essentially, these two equations are the same as each other, just with a different constant worked in there. And so you can use these equations to calculate the frequency of a photon that would be emitted. That could be related to the wavelength, or you could just calculate the difference in energy levels and match that to the energy of a photon that is emitted. So you want to have this picture of an atom in mind where it's got a nucleus in the middle and different quantum levels, N1, N2, N3. As we step out to higher quantum levels, there's our N3, and there's our N4, and there's our N5. So as we step up to higher or lower quantum levels, we'll see that there's a difference in energy. There's a difference in the atomic radius for electrons at these different quantum levels. And so if we had an electron jumping from, let's say, the n equals 4 level down to the n equals 2 level, we would emit a characteristic photon at a specific frequency of light, and that would match a specific energy of the transition. And this is why we end up seeing absorption and emission spectra at specific energies, specific lines in the spectra. As researchers began to discover these transitions, they named the different series of transitions after the scientists that were researching them. So a Lyman series transition would always have a final n value of 1. Anytime that you have an electron transitioning down to the n equals 1 level, we call that a Lyman transition. And similarly, we have Balmer for the n equals 2 being the final quantum level, and Paschen series for the electronic transitions where the electron jumps down to a final quantum level of n equals 3. So we can use absorption and emission spectra to ultimately study the atoms and elemental composition of different materials based on how they absorb or emit light. So let's take a look at the sun's emission spectrum. Essentially, this can tell us about different elements that are present in the sun. And so here's the spectrum shown in the top right here, and we have a series of different lines, A, B, C, E, F, G, and it's actually quite a complex emission spectrum. It has a lot of different light that's emitted, but only specific wavelengths of light are not allowed to be emitted from the sun. Those wavelengths of light are absorbed by the atmosphere of the sun and the elements in the sun. So this line C right here, somewhere around 650 nanometers, correlates to hydrogen in the atmosphere of the sun. So hydrogen is correlated with line C in the spectrum, and that's at a wavelength of somewhere around 656.3 nanometers. And so we're told that this is a transition between two states. The electrons in the atoms, in the atmosphere of the sun, are jumping between two different states, and that is why they end up being absorbed by the elements in the sun, and we do not see those wavelengths in the emission spectrum when we measure the sun's emission spectrum down here on Earth. And so we are told that one of the energy levels for this transition, this line C transition, is n equals 2, but we don't know if that's the initial or final quantum number that our electron is transitioning to. And we're asked to figure out what is the other state for this transition. That means the other n also equals question mark. So we need to figure out what our n initial and n final is for this transition. So first, let's calculate the energy of this transition. Here we have an energy transition with two different energy levels, and it's a specific photon at 656.3 nanometers of wavelength. So we should be able to calculate what the energy is of that transition. Remember, HC, a convenient equivalence is that H times C is 1240 EV nanometers, and so we can just divide by the number of nanometers here to get the EV of this transition. Here, our energy of this specific transition is 1.89 EV. And so now we can begin to ask ourselves, how does this relate to n equals 2? Could this possibly be the jump from the n equals 2 to the n equals 1 system? Well, let's try going ahead and testing out what that number would be if we were to be going from the n equals 2 to the n equals 1 states. And so if this was our transition, if we were jumping from the n equals 2 to the n equals 1 state, that would be a difference of 10.2 EV, and that does not match what we got for this transition. So we do not have n equals 1 involved in this transition. That is not involved in this transition. So this transition is going to somehow involve n equals 2 coming from or going to a different energy. So we know our energy transition needs to match 1.89 EV. Let's go ahead and plug that into our transition energy equation and see if we can solve for the final n value. And so for this calculation, I'm getting that the final n value for this particular transition is n equals 3. All right, so something weird is going on here. We have photons that were capable of hitting electrons and ejecting them. In other words, our light is experiencing collisions rather than reflection and transmission. And so it seems like light is capable of acting like a particle composed of photons. But previously, we learned that light was a wave. Light can experience superposition. Light can reflect or transmit into a medium. Light can have an interference pattern when it interacts with obstacle or opening on the same size scale as its wavelength. So which is it? Is light a particle or is light a wave? And the uncomfortable truth is that it is neither and both at the same time. If we think about a diffraction experiment where we're shining a laser light through some slits, we expect to see an interference pattern. So what happens if we reduce the intensity of that light until we're just shining through an individual photon, one photon at a time? I'm just going to shoot one photon through this diffraction slit window one at a time. And we notice that when we send one photon through one at a time, that ultimately we do not really see an interference pattern. It's only after we shine many, many photons that we eventually see the interference pattern start to emerge. And furthermore, if we set up a double slit experiment where we try to put like a little gate at each opening in that double slit, and we try to measure which slit the photon actually went through, when we set up the sensor on one slit, the photon will always go through the other slit that we weren't measuring, which is weird. We would expect that if the photons are going through one slit or the other, that we would eventually measure them as entering through one slit or the other. But when we actually set up our experiment to measure one slit in particular, all of the photons go the other way. It's like when we choose not to look at the photons and just look at the overall wave nature of light, that we see an interference pattern emerge. But when we choose to look at the individual photons and try to map out where they're going, where the particles are going, all of a sudden their wave-like nature collapses, and instead the light is just behaving like a set of billiard balls that would just be going through a single slit. And this is a very strange idea. Essentially, since these are quantum mechanical experiments, the fact that we are merely trying to measure them changes the outcome of the experiment. Under certain conditions, light behaves like a wave, and under other conditions, light behaves like a particle. We call this wave-particle duality, where a quantum mechanical object can seem to have particle-like nature or wave-like nature depending on how we choose to set up our experiment. So if light can behave like a wave or a particle, and it interacts with matter in different ways depending on how we choose to look at it, well, what is there to say that matter cannot behave like a particle and a wave at the same time? This is a very difficult idea to get your head around, but this is simply the case of the bizarre nature of quantum mechanics. When we shrink down to the scale of the quantum mechanical world, our classical physics representations that we understand in the macroscopic world no longer start to make sense, and instead things start to behave a little bit different. DeBroglie proposed that even matter can be said to have a wavelength. So the electron is orbiting around the nucleus, and it can only orbit around the nucleus at specific values. It's like there's a sweet spot for our electron to be orbiting around where it likes to sit and where it resonates. In fact, we had another situation like this in the past where only certain states were allowed for a system. And I'm talking about standing waves, where when we had standing waves, only certain patterns were allowed to emerge based on the rules of how that physical system worked. And the same type of allowed energy states are allowed for electrons orbiting around the nucleus. And we can say that their different orbital patterns can be correlated to different standing wave patterns. And in this way, an electron orbiting around the nucleus is a lot like a wave that sort of repeats itself, a standing wave with a fixed energy amplitude and a specific wavelength. The de Broglie wavelength can be calculated by taking Planck's constant and dividing it by the momentum, p, of the system. The momentum can be calculated for massive particles as being the mass times the velocity of that particle. So essentially, the more massive it is and the faster moving it is, the greater its momentum will be. But we know that certain particles, like photons, don't actually have mass. And so for the momentum of a photon or a massless particle, we will need to use the momentum being the energy divided by the speed of the object. So depending on the speed and mass of a quantum mechanical particle, it might have a wavelength and it might experience diffraction. In 1927, Thomson noticed that when shining an electron beam, not a photon beam, but an electron beam at a crystal, that the electrons themselves diffracted around the atoms in that crystal. The atoms in the crystal are very small and they're in a regular pattern, much like a diffraction grating. And so electrons themselves bend around different atoms within a crystal lattice and create a diffraction pattern, just like we saw with light interacting with small objects. And ultimately, this idea of the wavelength of electrons gives rise to advanced scientific techniques like electron microscopy. So let's try calculating the DeBroglie wavelength. If every particle and object in the world can be said to have a wavelength, then we should be able to use the DeBroglie wavelength to calculate the wavelength of that object. So let's think about a 0.5 kilogram basketball thrown at about 10 meters per second and compare that to the DeBroglie wavelength of an electron with kinetic energy of 1 eV. So we recall that the momentum for a massive object, anything with mass, can be said to have a momentum that is equal to mass times velocity. So the wavelength of the basketball could be calculated as Planck's constant divided by the mass of the ball times its speed. Remember, the units of Planck's constant are joule seconds. We're going to use joule seconds because that'll keep us in the units of meters for this wavelength. And to calculate the wavelength of an electron, we're going to need to figure out how fast that electron is moving first. If its kinetic energy is equal to 1/2 mv squared, and we have our mass of our electron being 9.11 times 10 to the negative 31 kilograms, that's a pretty small mass, we should be able to calculate its velocity. And in this formula, if you end up plugging in those numbers with the kinetic energy being 1 eV or 1.6 times 10 to the negative 19 joules, we get a velocity of our particle that is 5.9 times 10 to the 5th meters per second. And now if we plug in these values, we should be able to get a wavelength for these two objects. So the wavelength of our ball ends up being 1.3 times 10 to the negative 34 meters, and the wavelength of our electron becomes 1.23 times 10 to the negative 9 meters. This is about 1 nanometer, whereas the wavelength of the ball, I don't even know what to call that. That's an extremely small wavelength, smaller than any size scale that we could even possibly imagine. This is smaller than a single atom. And this is why large objects like a basketball moving with a pretty high speed, 10 meters per second, do not experience diffraction. A basketball will not experience diffraction because its wavelength is so unbelievably small, according to the de Broglie hypothesis. However, an electron has a wavelength of about 1 nanometer, and we could structure an object at about that size scale. Atoms are somewhere around the size of nanometers, and so an electron will interact with those objects and potentially experience diffraction because we could have an object on the same size scale as the wavelength of the electron. So thinking about this experiment with electrons having a wavelength and experiencing a diffraction, we can ultimately ascertain something about how fast the particle was moving or where it was located at some point in time. If we think about a single slit experiment and we send particles toward that single slit, whether they're photons or electrons, as we try to make that slit smaller and smaller, as we decrease our delta Y number, we eventually are able to locate where the particle is at a particular instance in time. It will guaranteed be going through that slit at some point in time. But as we shrink down that slit, we notice that the spread in the interference pattern gets greater. And so we could say something about how fast the particle was moving and in what direction it was moving as it passed through that slit. And we find that as we shrink down the size of the slit, that the spread of the interference pattern on the other side gets larger. That's how diffraction experiments work. And that ultimately implies that the momentum of the particle could have covered a larger range of possible momenta to go through that slit and give that interference pattern. Essentially, as we shrink down our position, we get a larger spread in the momentum of our particles when they go through that slit. They could either be in the middle, or maybe they could spread out because the central maximum is rather broad as we get a smaller diffraction slit. And essentially, this all gets at the idea of the Heisenberg uncertainty principle, which is a law of nature. This says that we can never truly know the position of a quantum mechanical object at the same time as knowing something about how it behaves, its motion, its momentum. And so the Heisenberg uncertainty principle can be separated into thinking about different dimensions, x, y, or z, and those are all independent of each other. But what we can say for this example, as we shrink down our delta y, as our delta y gets smaller, we notice that our delta p gets greater. And the Heisenberg uncertainty principle says that the product of the uncertainty in position times the uncertainty in momentum will always be greater than or equal to this value, Planck's constant, divided by 4 pi. In other words, there is no way that we can ever perfectly know where a quantum mechanical particle is at the same time as knowing how it is behaving. If we know more about the position, we know less about the momentum. If we know more about the momentum and how the particle is moving at a point in time, we actually know less about where it is actually located. And so we can use the Heisenberg uncertainty principle to ultimately dictate the relationship between our uncertainties in position and momentum. So previously we said something about the wavelength comparing macroscopic and microscopic objects. Let's think about how we can compare the uncertainties of macroscopic and microscopic objects. Here we have an electron and a bowling ball with a precision in their speed given to 1 millimeter per second. How do the position uncertainties compare for these two objects? So if we take a look at Heisenberg's uncertainty principle, we see that the uncertainty in position is related to the uncertainty in momentum and some constant value. So we can think about the uncertainty in the momentum as being mass times the uncertainty in the velocity. Since the mass of these objects is constant and the momentum is equal to m times v, we can ultimately substitute that for the uncertainty in the momentum, and that will always be bounded by Heisenberg's uncertainty principle. And so now we can go ahead and calculate a delta x for our ball, how uncertain our position would be for our ball based on the numbers that we've been given. And we can calculate the uncertainty in our position for an electron based on our uncertainty in speed for that electron. And so let's go ahead and plug in these numbers and see how the uncertainty in position for these macroscopic and microscopic objects compare. So our uncertainty in position for the ball is very small. In other words, for a macroscopic object, we can very easily tell where that object is based on its mass and momentum. However, the small object, the electron, is moving at with the same uncertainty in its speed, and we have a much greater uncertainty in our position, and so it is much more difficult to tell exactly where that small quantum mechanical particle is given this uncertainty in its speed because of its small mass. So things should be feeling a little bit weird by now. All of the things that we're talking about sort of go against the previous understanding of classical physics. We thought light was a wave. It turns out that sometimes it behaves like a particle. We thought matter was a particle, but it turns out sometimes it behaves like a wave. And so this entire framework of quantum mechanics is different, a different way of thinking, a new regime of thinking as compared to classical physics. And what we can say is for macroscopic objects, classical physics tends to work pretty well. Our quantum mechanical phenomena are not observed because these macroscopic objects have small DeBroglie wavelengths and ultimately a small uncertainty in the values of their position and motion. However, when we shrink down to the microscopic scale, the nanoscopic scale, thinking about photons and electrons, quantum mechanics takes over and classical physics doesn't quite work for explaining what's going on. To further understand the quantum mechanics of electrons in an atom, we need to label the quantum numbers of an electron within an atom. These are essentially labels that we use to keep track of electrons within a specific atom. And there are 4 quantum numbers that you need to know about. The first is n, the principal quantum number, which essentially dictates the radius and energy of an electron in a particular orbital of an atom. Due to the quantization of these orbitals, electrons can only rest at specific energy levels, and we would say that the principal quantum number n can only adopt integer values greater than 0. The next quantum number that we have is L, the angular momentum quantum number. And essentially, this is dictated by the fact that electrons can only have a specific angular momentum when they are present in an atom. And the L numbers can adopt any integer values, including 0, up to what the N number is, -1. So we have specific rules for which quantum numbers are allowed, and we cannot have our L number exceed our N number in this case. The next quantum number is the magnetic orbital quantum number, m sub L. M sub L is specifically focused on the orientation of these orbitals relative to a magnetic field created by the motion of those electrons. And so m sub L can always adopt values that are integer values ranging from -L to +L. That means that we can have m sub L numbers that are equal to -L, and then we add 1 all the way up to that number through 0, and then continue adding 1 to our quantum number m sub L until the maximum quantum number m sub L that is allowed would be a value of +L. Finally, we have the spin quantum number m sub S, which is essentially talking about the way that electrons can only ever spin one of two ways. They can only ever spin up, or they can only ever spin down according to our right-hand rule. And each of the spins of those electrons creates a small intrinsic spin magnetic moment, and that ultimately dictates how electrons can reside in the orbitals of an atom. The m sub S number can only ever be +1/2 or -1/2. And it's important to say that photons cannot actually have a spin, but protons and electrons can have a spin, and they can only ever have one of two values for that spin quantum number m sub S. And so as we start from hydrogen on the periodic table and continue adding electrons and protons to create the elemental structure of a higher level atom on the periodic table, we need to fill electron orbitals according to the electron orbital filling order. Here's the order sort of shown to you in a diagrammatic representation. We always start at the lowest values of n, the lowest energies when we're filling our electron orbitals around an atom, and that's called the Aufbau principle. Essentially, electrons will always fill the lowest n value that they can before filling up higher energy orbitals at higher n numbers. Hund's principle says that the electrons will occupy a minimum energy state and ultimately half occupy those energy states before they fully occupy them with a paired spin. So essentially, our electrons will fill each orbital with one electron in the orbital first, all with the same direction of spins, before they pair electrons within those orbitals so that the spins are paired. The Pauli exclusion principle says that each orbital can only have 2 electrons in it with each spin value. There can only be 1 spin up and 1 spin down electron within a particular orbital. And so ultimately this dictates how orbitals are filled by electrons and how we know that electrons can only occupy certain orbitals in an atom. And you sort of want to have this visual of the s orbitals, the p orbitals, the d orbitals, and the f orbitals within an atom. And essentially this is all for one n level. We would first fill our electrons in here with 1 electron spin up and then 1 electron spin down, and then we would fill each of these p orbitals with 1 spin up electron before we paired them with 1 spin down electron, and then we would fill the d orbitals in that order as well. So the periodic table is closely related to the quantum mechanical nature of atoms. A shell is a group of atomic orbitals with the same quantum number n. And a subshell is a set of orbitals within that shell n that has the same quantum number L, the same angular momentum quantum number L. So the shell designations would include numbers like n equals 1. That's called the K shell. And those are the smallest energy orbitals in an atom. And so you can sort of envision them as this tight blue circle with other electrons orbiting around in every which way, only at allowed energy states. The n equals 2 shell is called the L shell. The n equals 3 is the M. 4 is n, and so on. And as we get to higher shell quantum number n's, then the electron orbitals get larger in radius and have a larger energy. Within each shell, we can have orbitals that are filled like the s orbitals, p orbitals, d and f orbitals, and each of those orbitals corresponds to a specific orbital angular momentum quantum number L, where L equals 0 corresponds to the s block on the periodic table where we're filling s orbitals. L equals 1 corresponds to the p block where we are filling p orbitals. L equals 2 corresponds to the d block where we're filling d orbitals. And L equals 3 corresponds to the f block where we're filling f orbitals. And remember, we can hold 2 electrons in each of these suborbitals within a single orbital block. And so the number of electrons can change based on which orbital you're in. This also says something about the periodic table trends for ionization energy and atomic radius for different elements on the periodic table. Essentially, based on how electrons fill the orbitals within an atom, they will have differing energy for their outermost electron. Some atoms have a very high ionization energy required to pluck an electron off of that atom, and that's because the electron is in a very stable energy state. So for hydrogen, we know our ground state electron is at a energy of negative 13.6 eV, so the ionization energy to pluck off that electron would require 13.6 eV. For different atoms, they have different stabilities based on how their electrons fill the orbitals. So for helium, the ionization energy is very large, and we'll notice for all of the noble gases that the ionization energy is relatively large compared to other elements near it on the periodic table. And that's because noble gases are very stable and their electrons reside in very stable, low energy configurations. The atomic radius, of course, increases with increasing n numbers. So as we go to lower rows on the periodic table, we're going to higher energy levels, higher n numbers, and we see that the atomic radius essentially increases as we go down on the periodic table to higher quantum numbers n. So we've spoken about hydrogen-like atoms and how they can be modeled to have quantized energy levels that the electrons reside in. But for more complicated atoms than hydrogen-like atoms, we need to think about how multiple electrons will affect the outermost electron's energy. And essentially, the effective nuclear charge is the positive charge that would be felt by the outermost electron, which is ultimately shielded a little bit by other inner core electrons. Essentially, as we have electrons on the inside of an atom that are stable, they shield out some of that positive charge from the nucleus, ultimately weakening the effective nuclear charge that is felt by the outermost electron. And this means that the energy dynamics of that outermost electron will be affected by the effective nuclear charge of this shielded proton, this shielded nucleus. And we can calculate the energy of an electron at a specific quantum level n for a multi-electron atom by thinking about its effective nuclear charge in the energy equation that we've seen previously. And so here are some values for the effective nuclear charge for various alkali metals that you might need to solve for. Usually the effective nuclear charge will be given to you in this class. So here we are ready to calculate the energy of an electronic transition for an element with multiple electrons, shielding the outermost electron from feeling the total nuclear charge in the nucleus. Here we have lithium, which is experiencing a nuclear effective charge that was given in the previous table of 1.26. That's the effective nuclear charge. And so when we're calculating the transition from an n equals 2 to n equals 4 state, we can plug it in directly into our energy transition equation. But now our energy for these shielded electrons looks a little bit different. We have Z effective out in front squared times E0. And now we would have 1 over n final squared minus 1 over n initial squared. And so if we plug in our numbers, we can get a result for this electronic transition, which would be different for lithium rather than for hydrogen. So here for this energy transition, I'm getting an energy of 3.213 EV. That would be the energy absorbed as we transition from the n equals 2 to the n equals 4 state in lithium with multiple electrons. So that'll cover everything for our unit on quantum mechanics. Some of these ideas are a little bit difficult to wrap your head around, so please do take some time to understand the equations, because this stuff will definitely come up in our next 2 units on atomic physics and nuclear physics. Thanks for sticking around. I'll see you in the next one.